On July 1st, 2025, telescopes detected something impossible, hurtling toward our Sun at 245,000 kilometers per hour. 3I Atlas became only the third confirmed interstellar object ever discovered, but this visitor carries disturbing secrets. Scientists estimate it's 7 billion years old, 3 billion years older than Earth itself. Within hours, SETI telescopes locked onto the object, scanning for artificial signals. What if this ancient wanderer isn't arriving by chance? What if our century of radio broadcasts into space finally received an answer? The evidence will shake you. Hit subscribe and prepare yourself. We begin. The NASA-funded Atlas Survey Telescope in Chile registered an anomaly on July 1st, 2025. Automated systems flagged a rapidly moving object with an impossible trajectory, one that clearly originated from outside our solar system. Within 24 hours, follow-up observations confirmed humanity's worst fear and greatest hope. We had spotted our third confirmed interstellar visitor. Unlike the previous two visitors, 1I Oumuamua in 2017 and 2I Borisov in 2019, this newcomer displayed characteristics that defied every astronomical model. Initial tracking data revealed an orbital eccentricity of 6.141, the highest ever recorded for any interstellar object. This extreme eccentricity made its trajectory appear almost perfectly straight rather than curved, like a cosmic bullet fired directly at our solar system. Amateur astronomer Sam Dean noted that earlier Atlas observations from June 5th through 25th had been overlooked because the object passed in front of the galactic center's dense star fields. The cosmic visitor had been deliberately hiding in the brightest, most crowded region of our night sky. This incoming direction, oriented toward the Milky Way center, made detection nearly impossible until the final moment. Was this coincidence or calculated concealment? By July 2nd, observatories worldwide confirmed the object's cometary activity, a faint coma and potential tail emerging as solar radiation began affecting its surface. The Minor Planet Center officially designated it 3I Atlas, marking it as the third confirmed interstellar object in human history. Within hours of the announcement, 122 observations had been collected from 31 different observatories across 6 continents. The global astronomical community mobilized with unprecedented urgency. Dr. Simon Steele of the SETI Institute hosted an emergency broadcast featuring University of Washington astronomer Dr. James Davenport and SETI researcher Dr. Ariel Graykowski. Their message was clear. This wasn't just another space rock. Unlike 1I Oumuamua, which was discovered after its closest approach to the Sun, 3I Atlas had been caught on its inbound journey, providing humanity with months of observation time. The object's retrograde orbit, moving backward relative to planetary motion, added another layer of cosmic impossibility. Its trajectory tilted 175 degrees with respect to the ecliptic, meaning it approaches from the opposite direction of everything else in our solar system. This retrograde approach, combined with its perihelion speed of 68 kilometers per second, creates a relative velocity difference with Earth of 98 kilometers per second. Something about 3I Atlas felt different from the moment of discovery. Astronomers immediately recognized they were witnessing something unprecedented, not just another wandering comet, but potentially the oldest object ever observed. Matthew Hopkins and his Oxford colleagues estimated with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old, based on typical ages of stars in the thick disk. The implications struck the scientific community like lightning. We weren't just observing a visitor from another star system, 2C. We were potentially watching the approach of something that witnessed the birth of galaxies. 3I Atlas blazes through space at an incomprehensible 245,000 kilometers per hour. making it the fastest object ever detected in our solar system. This velocity shatters every previous record and challenges our understanding of interstellar mechanics. The object maintains a hyperbolic trajectory with an eccentricity of 6.141 Burr, far exceeding the previous record holder, 2I, Borisov, which registered only 3.4. To put this speed in perspective, our fastest spacecraft, Voyager 1, travels at approximately 61,000 kilometers per hour. 3I Atlas moves 4 times faster than humanity's most advanced interstellar probe. This tremendous velocity creates a relative speed difference of 98 kilometers per second between Earth and the approaching object. Such speeds make any potential human intercept mission completely impractical using current chemical rocket technology. The mathematical implications are staggering. Scientists calculate that 3I Atlas has been wandering through interstellar space for potentially millions, if not hundreds of millions, of years. During this cosmic journey, gravitational encounters with stars and stellar nurseries accelerated the object through repeated slingshot effects. Each stellar encounter added momentum, building the tremendous velocity we observe today. The object's speed becomes even more remarkable when traced backward through galactic coordinates. When 3I Atlas arrived at our solar system, it was moving away from the galactic center with a velocity of negative 51 kilometers per second relative to the Sun. Simultaneously, it was moving upward through the galactic plane with a velocity of positive 18.5 kilometers per second. This vertical velocity component is remarkably high compared to nearby stars and other interstellar objects, indicating that 3I Atlas follows a tilted orbit around the Milky Way. Such an orbital pattern suggests the object belongs to the thick disk population, an ancient stellar neighborhood composed primarily of older stars with lower heavy element concentrations than our Sun. The thick disk connection led Hopkins and his team to estimate the object's age at potentially 7 to 14 billion years. The speed also reveals something unsettling about cosmic mechanics. Astor Taylor from the University of Michigan noted that objects like 3I Atlas actually pass through solar systems constantly. Hopkins estimates that approximately 80 objects the size of Oumuamua pass through Jupiter's orbit every year. They're simply too small and fast to detect unless they approach very close to Earth. This raises a chilling question. How many other high-speed visitors have passed through our solar system undetected? The Vera Rubin Observatory expects to discover at least one interstellar visitor per year once fully operational. Future surveys may reveal dozens of these cosmic wanderers at greater distances from the Sun before solar heating triggers any cometary activity. 3I Atlas represents just the tip of an interstellar iceberg. Its record-breaking speed serves as humanity's wake-up call to a universe filled with ancient, fast-moving objects that could approach from any direction at any time. The question that haunts astronomers: what could accelerate an object to such incredible speeds? And why does its trajectory seem so deliberately aimed? 3I Atlas joins an exclusive club of confirmed interstellar visitors, following 1I Oumuamua in 2017 and 2I Borisov in 2019. Each interstellar object has presented unique mysteries, but 3I Atlas breaks every pattern established by its predecessors. Early estimates suggest the comet could be up to 20 kilometers in size, making it over 100 times bigger than Oumuamua. This enormous size defies models predicting typical dimensions for interstellar debris. Unlike its predecessors, which appeared as single objects with relatively simple characteristics, 3I Atlas displays complex, active features that suggest internal processes. Hubble Space Telescope observations reveal a teardrop-shaped dust cocoon streaming from the object's nucleus, indicating active material ejection. The Rubin Observatory team discovered that the apparent coma grew during their 2-week observation period, with the nucleus spanning an estimated 11.2 kilometers. Strangely, Rubin observations show hints of a dusty tail that points directly toward the Sun, opposite to typical comet behavior. Normally, solar radiation pushes comet tails away from the sun, but 3I, Atlas, appears to be ejecting massive particles in the solar direction that are too heavy to be affected by radiation pressure. This anomalous tail direction suggests deliberate material ejection rather than passive solar heating. The timing pattern emerges as equally unsettling. Oumuamua was discovered after its closest approach to the Sun during its outbound journey from our solar system. 2I. Borisov was also detected relatively late in its solar approach, limiting observation opportunities. 3I. Atlas breaks this pattern by being discovered well before its October 29th perihelion, providing unprecedented observation time during its inbound approach. The controversial Harvard astrophysicist Avi Loeb previously suggested that Oumuamua might have been artificial technology rather than a natural object. His claims generated significant scientific skepticism, with most astronomers dismissing the artificial hypothesis as speculative. However, Loeb and his colleagues have now published similar speculation about 3I, Atlas, arguing its characteristics are even more suggestive of technological origin. The frequency of interstellar visitors appears to be increasing, though this might reflect improved detection capabilities rather than actual increases in cosmic traffic. Hopkins notes that smaller interstellar objects likely pass through our solar system regularly. We simply lack the technology to detect them unless they approach very close to Earth. The Vera Rubin Observatory should dramatically improve detection rates, potentially finding one interstellar visitor per year on average. Each interstellar visitor teaches us something new about galactic mechanics and cosmic history. While Oumuamua and Borisov originated from different regions of space, 3I, Atlas, appears to come from the thick disk, a galactic region associated with older stellar populations. This thick disk origin suggests 3I, Atlas, has been wandering the galaxy for potentially billions of years before its chance encounter with our solar system. The progression from Oumuamua through Borisov to 3I, Atlas, reveals an escalating pattern of cosmic strangeness. Each visitor displays more complex characteristics and raises more disturbing questions about what might be traveling through the dark spaces between stars. What message might these three cosmic messengers be carrying? Scientists estimate 3I, Atlas, has approximately a 67% chance of being more than 7.6 billion years old, while our Sun, solar system, and its comets formed only 4.5 billion years ago. This age estimate makes 3I, Atlas, potentially the oldest object ever observed by human science. Researchers believe it could be as much as 14 billion years old, approaching the age of the universe itself. The implications of encountering such an ancient traveler extend far beyond simple astronomical curiosity. The age estimates derive from 3I, Atlas's association with the Milky Way's thick disk population, a vertically extended region containing the galaxy's oldest stars. The object's high vertical velocity component of positive 18.5 kilometers per second relative to the Sun indicates it belongs to this ancient stellar neighborhood. Thick disk stars typically have lower concentrations of heavy elements compared to younger stellar populations, suggesting they formed when the universe contained fewer processed materials. During its potentially billions of years wandering through interstellar space, 3I, Atlas, experienced gravitational encounters with countless stars and stellar systems. Each encounter modified its trajectory and increased its momentum through gravitational slingshot effects. The longer an object spends in interstellar space, the faster it moves due to these accumulated gravitational boosts. 3I, Atlas's tremendous speed serves as a cosmic odometer, recording eons of galactic travel. The thick disk connection raises profound questions about what 3I Atlas might have witnessed during its cosmic journey. If the object truly dates back 7 to 14 billion years, it predates the formation of most planetary systems in our galactic neighborhood. It could have been present during the era when the first heavy elements were being forged in stellar cores and distributed through supernova explosions. Such an ancient object might carry pristine samples of early universe materials within its structure. David Jewett from UCLA noted that determining where the comet originated is nearly impossible, comparing the task to glimpsing a rifle bullet for 1,000th of a second and trying to project backward to find where it started. However, computer models suggest 3I, Atlas, likely originated from a star system that no longer exists in its original form. Its parent star could have evolved through its entire life cycle, possibly ending as a white dwarf, neutron star, or black hole. The age implications become even more staggering when considering cosmic evolution. 14 billion years ago, the universe was less than 1 billion years old and contained far fewer heavy elements necessary for planet formation. If 3I, Atlas formed during this era, it represents a direct sample from the universe's chemical infancy. Its composition might reveal secrets about stellar nucleosynthesis and galactic chemical evolution that occurred before our solar system existed. The psychological impact of encountering such ancient matter cannot be understated. Every atom in 3I, Atlas, potentially predates every atom in the human body by billions of years. We are essentially watching a cosmic time capsule that has been traveling through space since before Earth's formation. The humbling realization that this object has been journeying through the galaxy longer than complex life has existed on Earth forces us to reconsider our place in cosmic history. What cosmic secrets might this ancient wanderer be carrying toward our young solar system? Within hours of 3I, Atlas's confirmation as an interstellar object, the SETI Institute initiated unprecedented monitoring protocols. Dr. Wael Farah, SETI chair and Allen Telescope Array project scientist, led emergency observations targeting both narrowband emissions that could indicate artificial signals and natural radio emissions from dust and molecular compounds. The speed and intensity of SETI's response reveals how seriously researchers are taking the possibility of non-natural origins. The Allen Telescope Array team began monitoring on July 2nd, just one day after the initial discovery announcement. Within 1 week, they had collected over 21 terabytes of data, equivalent to thousands of hours of high-resolution video. This massive data collection effort represents one of the most comprehensive attempts to detect artificial signals from any astronomical object. The dataset remains under active analysis, with researchers systematically searching for both natural radio signatures and hypothetical technosignatures. Scientists are specifically monitoring for several types of artificial signals that would indicate technological origin. Primary targets include radio communications, electrostatic discharges caused by sunlight hitting artificial surfaces, and any signs of maneuvering or propulsion. An active probe might attempt to correct its course or reposition antennas to maintain communication with its origin point. The most definitive proof would be an approach to Earth in a stable orbit, as any decision-making intelligence would likely want to investigate our planet's water, atmosphere, and life. The monitoring effort extends beyond simple signal detection to comprehensive spectroscopic analysis. Large observatories, including the Vera Rubin Observatory, are conducting detailed spectroscopic studies to determine 3I, Atlas's chemical composition. These studies will reveal whether the object contains exotic compounds not commonly found in solar system comets. Unusual chemical signatures could indicate artificial construction materials or propulsion systems. SETI's interest in 3I, Atlas, extends beyond simple curiosity to address fundamental questions about extraterrestrial intelligence. Avi Loeb and his colleagues have proposed that the object might provide evidence supporting the dark forest hypothesis, the idea that intelligent civilizations remain silent to avoid detection by potential predators. This hypothesis suggests that the cosmic silence observed by SETI isn't due to lack of intelligent life, but rather civilizations actively hiding from mutual destruction. The SETI response also includes preparation for potential communication scenarios. Loeb has suggested that if 3I Atlas proves to be artificial, humanity should consider attempting radio communication during its approach. However, he warns that such communication carries risks, an alien intelligence might perceive artificial signals as threats and respond defensively. The proximity of 3I, Atlas, makes this scenario potentially dangerous, as any response could reach Earth within months rather than thousands of years. Loeb has tasked the Galileo Project research team to monitor for enhanced unidentified anomalous phenomena activity using 3 observatories immediately after 3I. Atlas approaches perihelion on October 29th. This monitoring strategy anticipates the possibility that 3I, Atlas, might deploy smaller probes toward Earth and other planets during its closest solar approach. Now, here's where you come in. Comment below where you're watching from and what time it is in your location. While you're at it, hit that like button and subscribe. We need every sharp mind following this story as it unfolds. Stay sharp, the journey only gets stranger. Harvard astrophysicist Avi Loeb and his colleagues Adam Hibbard and Adam Crowell from the Initiative for Interstellar Studies published a controversial paper suggesting 3I, Atlas, might be alien technology. Their paper explores the possibility that this interstellar visitor provides evidence supporting the dark forest hypothesis, the terrifying idea that our cosmic neighborhood is filled with intelligent civilizations hiding from hostile predators. The academic community's reaction has been swift and polarized. Loeb points to several anomalous characteristics that challenge natural explanations for 3I, Atlas. Based on brightness measurements and assuming low reflectivity, the object measures approximately 20 kilometers in diameter, over 100 times larger than Oumuamua, and vastly exceeding model predictions for natural interstellar debris. Despite its comet-like designation, there are no clear signs of the coma or tail expected when icy objects approach the Sun. Interstellar comets typically outgas when solar heating occurs, as demonstrated by 2I, Borisov, making this absence highly unusual. The timing of 3I, Atlas's planetary approaches presents another compelling anomaly. The object's trajectory brings it unusually close to Venus at 0.65 astronomical units, Mars at 0.19 astronomical units, and Jupiter at 0.36 astronomical units. The cumulative probability of such close approaches, given the object's orbital parameters but random arrival time, calculates to only 0.005%, a remarkably improbable coincidence. Loeb suggests this synchronized approach to multiple planets indicates deliberate targeting rather than chance encounter. Perhaps most intriguingly, 3I, Atlas, will be hidden behind the Sun from Earth's perspective during its October 29th perihelion passage. This solar eclipse creates perfect conditions for a reverse solar Oberth maneuver, a propulsion technique where spacecraft thrust is applied at maximum orbital speed to achieve maximum kinetic energy change. Such a maneuver could slow the object from its tremendous interstellar velocity, allowing it to become gravitationally bound to our solar system. The fact that this optimal braking opportunity occurs precisely when Earth cannot observe, it raises disturbing questions about intentional concealment. The scientific community has reacted with significant skepticism to Loeb's artificial origin hypothesis. Chris Lintott from Oxford University, who participated in modeling 3I, Atlas's galactic origins, called any artificial suggestion nonsense on stilts and an insult to the exciting work going on to understand this object. Other astronomers have criticized the paper for making extraordinary claims without extraordinary evidence. Loeb defends his position by characterizing the paper as a pedagogical exercise, an intellectual thought experiment worth exploring, regardless of its ultimate validity. He argues that the hypothesis provides interesting insights that could apply to the dozens of interstellar objects expected to be discovered by the Vera Rubin Observatory over the next decade. Loeb also notes that discussions about external artificial intelligence threats receive far less attention than discussions about terrestrial AI risks, despite both representing potential existential threats. The dark forest implications add another layer of cosmic dread to the artificial hypothesis. If civilizations throughout the galaxy are indeed hiding from predatory intelligences, 3I, Atlas, might represent either a scout from such a predator civilization or a refugee from cosmic violence. The hypothesis suggests that uncertainty about relative strength between civilizations might favor hiding as a survival mechanism, especially for civilizations that have been bruised by previous encounters. Whether natural comet or artificial probe, 3I, Atlas has already succeeded in forcing humanity to confront uncomfortable questions about our cosmic isolation. 3I Atlas follows a trajectory synchronized to approach Venus, Mars, and Jupiter with mathematically improbable precision. The cumulative probability of such close planetary encounters, given random arrival timing, calculates to an astronomically low 0.0005%. These aren't casual flyby distances. The object will pass Venus at 0.65 astronomical units, Mars at 0.19 astronomical units, and Jupiter at 0.36 astronomical units. Such precision targeting defies the random wandering expected from natural interstellar debris. NASA confirms that 3I, Atlas, poses no threat to Earth, maintaining a closest approach distance of approximately 1.8 astronomical units, about 170 million miles. However, the carefully calculated distances to other planets suggest deliberate mission planning rather than coincidental trajectory. Marshall Eubanks from Space Initiatives has calculated that several interplanetary spacecraft and Mars orbiters will have clear views of 3I Atlas during its approach phases. These observations could reveal whether the object exhibits any course corrections during planetary encounters. The object's trajectory tilts 175 degrees with respect to the ecliptic plane, creating a retrograde approach that moves opposite to all natural solar system motion. This retrograde orientation aligns the object's path closely with the orbital planes of solar system planets. Such alignment represents a rare 0.2% probability occurrence, making the precise planetary targeting even more statistically remarkable. The mathematical odds against both alignment and timing, occurring by chance, are virtually impossible. The Jupiter encounter presents particular observational opportunities for spacecraft already positioned in the outer solar system. The Jupiter Icy Moons Explorer mission could potentially redirect instruments toward 3I Atlas during its 0.36 astronomical unit approach. NASA's Psyche spacecraft, currently traveling toward its namesake asteroid, will be positioned approximately 0.4 astronomical units from 3I Atlas during the encounter. These spacecraft observations might detect any artificial maneuvering or signal transmission during planetary approach. The feasibility of launching Intercept missions from Earth or Mars has been analyzed, though most launch windows have already passed. The object's tremendous speed creates a relative velocity of 98 kilometers per second with Earth, making chemical rocket intercepts completely impractical. Hypothetical flyby speeds would exceed 60 kilometers per second, making imaging during such encounters extremely challenging compared to typical planetary mission speeds. Mars-based observations offer unique advantages during the October period when Earth-based telescopes cannot observe 3I ATLS due to solar conjunction. Mars orbiters and rovers could provide critical observational coverage during perihelion when the object should display maximum activity. High-resolution imaging from Mars could reveal surface features, outgassing patterns, or potential artificial structures that Earth-based telescopes cannot resolve. The precision planetary targeting raises unsettling questions about intent and capability. If 3I ATLAS represents artificial technology, its trajectory suggests comprehensive knowledge of our solar system's planetary arrangement. The timing implies long-term mission planning that accounts for planetary positions and orbital mechanics with extraordinary accuracy. Natural objects lack the ability to calculate and execute such complex multiplanetary approaches. Loeb warns that the close planetary approaches create opportunities for 3 ATLS to deploy smaller probes toward individual worlds. Such probe deployment during planetary encounters would be virtually impossible to detect from Earth due to the small size and high speeds involved. the mathematical impossibility of coincidental precision forces an uncomfortable conclusion. Either we're witnessing the most improbable natural event in solar system history, or we're watching the execution of a deliberately planned mission. On October 29, 2025, 3I Atlas will reach perihelion, its closest approach to the Sun, at 1.36 astronomical units, positioned between Earth and Mars. Crucially, this closest approach occurs when the object will be completely hidden behind the Sun from Earth's perspective, creating a perfect solar eclipse that prevents terrestrial observation during the most critical phase of its visit. Even the Hubble and Webb space telescopes cannot point toward the Sun's glare to track the object during this period. The timing seems impossibly convenient for any activity requiring concealment. This solar eclipse provides ideal conditions for executing a reverse solar oberth maneuver, AFI, a propulsion technique where thrust is applied at maximum orbital speed to achieve maximum kinetic energy change. During normal oberth maneuvers, spacecraft accelerate at periapsis to maximize escape velocity, but a reverse maneuver applies braking thrust to slow down from high interstellar speeds. The optimal point for such velocity reduction to become gravitationally bound to our solar system occurs precisely at perihelion. The fact that this perfect braking opportunity coincides exactly with Earth's observational blackout raises disturbing questions about deliberate timing. 3I Atlas will remain invisible to ground-based telescopes through September 2025 due to its proximity to solar glare. The object should reappear for renewed observations by early December 2025, when it emerges on the opposite side of the Sun. This 3-month observational gap occurs during the period when any artificial technology would most likely reveal its true nature through maneuvering or probe deployment. Natural comets typically display their most dramatic activity during perihelion passage as solar heating vaporizes surface materials. While Earth-based observations will be impossible, several spacecraft positioned throughout the solar system could maintain visual contact during the critical period. Mars orbiters and rovers will have unobstructed views of 3I Atlas during its perihelion passage, potentially providing the only real-time observation of whatever occurs behind the Sun. NASA's Psyche mission and the Jupiter Icy Moons Explorer could also track the object from their distant vantage points. The observational blackout creates opportunities for activities that would be immediately detected if visible from Earth. Potential scenarios include deployment of smaller probes toward planetary targets, course corrections to achieve solar system capture, or transmission of signals to distant locations. If 3I Atlas represents artificial technology, its controllers would naturally choose the solar eclipse period for any operations requiring secrecy. Continuous observational coverage becomes crucial for detecting unusual activity, like fragmentation or probe separation. Astronomers regret the limited observations of previous interstellar objects, which were discovered relatively late in their solar system passages. The early discovery of 3I Atlas provides unprecedented opportunity for complete mission monitoring, except during the most critical 3-month blackout period. Loeb has assigned his Galileo project team to monitor for enhanced unidentified anomalous phenomena activity immediately after the October 29th perihelion passage. This strategy anticipates the possibility that any probes deployed behind the Sun might arrive at Earth and other planets in the months following perihelion. The team will use 3 dedicated observatories to search for artificial objects that might have been released during the hidden approach. The convenient solar eclipse timing forces uncomfortable speculation. Natural cosmic mechanics rarely provide such perfectly timed concealment opportunities. If 3I Atlas were randomly wandering through space, the probability of its closest solar approach occurring during Earth's observational blackout would be extremely low. What activities might unfold in the 3 months when human eyes cannot witness them? Despite approaching the Sun and experiencing increasing solar radiation, 3I Atlas displays no clear signs of the coma or tail expected from normal cometary outgassing. Interstellar comets typically develop dramatic outgassing, when solar heating vaporizes their icy surfaces, as clearly demonstrated by 2I Borisov during its 2019 visit. While some observers report marginal cometary activity, including a faint coma and potential tail-like elongation, these features remain far subtler than expected for an object of this size approaching the Sun. Vera Rubin Observatory observations reveal puzzling tail behavior that contradicts normal cometary physics. The detected dusty tail points directly toward the Sun rather than away from it, opposite to the expected direction caused by solar radiation pressure. This anomalous orientation suggests that massive particles are being ejected in the solar direction, too heavy to be influenced by radiation pressure at the object's current distance from the Sun. Such behavior implies active material ejection rather than passive solar heating effects. Initial observations in early July were unclear about whether 3I Atlas qualified as an asteroid or comet. Various astronomers, including Alan Hale, reported no obvious cometary features during the first detection period. Only follow-up observations on July 2nd by multiple observatories confirmed marginal coma development with potential tail elongation, measuring 3 arcseconds in angular length. David Jewett and Jane Liu, using the Nordic Optical Telescope, confirmed that 3I Atlas was clearly active, with a diffuse appearance, though activity levels remained modest. Researchers estimate that 3I Atlas is ejecting micrometer to millimeter-sized dust particles at velocities of approximately 0.1 to 1 meter per second. The calculated mass loss rate ranges from 0.1 to 1 kilograms per second, substantial material ejection that should produce more visible cometary features. The disconnect between calculated outgassing rates and observed visual activity suggests either unusual surface composition or non-thermal material ejection mechanisms. The absence of expected outgassing raises questions about the object's internal composition and structure. Natural comets contain significant amounts of water, ice, and volatile compounds that readily vaporize under solar heating. The limited outgassing from 3I Atlas suggests either depletion of volatile materials after billions of years in space or artificial construction from non-volatile materials. Both scenarios present unusual implications for understanding interstellar object composition. Spectroscopic studies planned by major observatories will determine whether 3I Atlas contains exotic compounds not commonly found in solar system comets. These chemical analyses could reveal whether the object formed under different conditions than typical comets or contains artificial materials. Unusual spectroscopic signatures might indicate either exotic formation environments or technological construction materials. The limited cometary activity becomes even more puzzling when considering the object's tremendous age and cosmic journey. After potentially billions of years wandering through interstellar space, exposure to cosmic radiation and micrometeorite impacts should have significantly altered surface composition. Such extended exposure typically creates protective crusts that inhibit outgassing, but the observed activity levels seem inconsistent with expected surface modification. The absence of normal cometary behavior eliminates one of the primary methods for distinguishing natural objects from artificial constructs. Without obvious outgassing signatures, astronomers must rely on other characteristics, like trajectory analysis, surface reflectivity, and potential signal emissions to determine the object's nature. The missing cosmic signature leaves 3I Atlas suspended in an uncomfortable classification limbo, too active to be a simple asteroid, yet too quiet to be a typical comet. Early size estimates suggest 3I Atlas measures approximately 20 kilometers in diameter, making it over 100 times larger than 1I Oumuamua, and vastly exceeding typical dimensions predicted for natural interstellar debris. Asta Taylor, from the University of Michigan, notes that determining exact size remains challenging, but current estimates place the object and its surrounding coma at up to 15 miles across. Vera Rubin observatory measurements estimate the nucleus itself spans 11.2 kilometers, confirming that even the solid core exceeds the total dimensions of previous interstellar visitors. This enormous size makes 3I, ATLS, significantly larger than both previous confirmed interstellar objects, which measured less than a mile in diameter. The size difference isn't marginal. 3I, Atlas, dwarfs its predecessors by factors that challenge theoretical models for interstellar object formation and ejection. Computational models predict much smaller typical sizes for debris ejected from star systems, making objects of this scale extremely rare. The statistical probability of detecting such a massive interstellar visitor approaches astronomical unlikelihood. Recent observations from the Vera Rubin Observatory confirmed that 3I, Atlas ranks as the largest interstellar object ever detected. The object transforms into a giant cosmic rainbow in telescope images, displaying spectacular visual characteristics during its approach. Striking Technicolor time-lapse photography reveals the object as a rainbow-colored string of cosmic pearls against the star field background. These dramatic visual presentations far exceed the subtle appearances of previous interstellar visitors. The massive scale creates significant implications for any potential artificial origin hypothesis. An artificial construct measuring 20 kilometers would represent engineering capabilities far exceeding current human technology. Such dimensions approach the scale of small asteroids or large spacecraft that could potentially house substantial populations or industrial facilities. The size alone doesn't prove artificial origin, but it demonstrates the scale of technology required if the object were indeed manufactured. The large size correlates with substantial material ejection rates measured through spectroscopic analysis. With calculated outgassing of 0.1 to 1 kilograms per second of micrometer to millimeter-sized particles, the object possesses sufficient mass to sustain such material loss over extended periods. However, the ejection velocities of 0.01 to 1 meter per second seem modest for such a large object under solar heating. This disconnect between size and activity levels adds another layer of mystery to the object's characteristics. The detection of such a large interstellar object raises questions about observation bias and the actual population of cosmic wanderers. Smaller interstellar objects likely pass through our solar system regularly, but remain undetected due to size and distance limitations. The Vera Rubin Observatory should dramatically improve detection capabilities for objects of various sizes, potentially revealing whether 3I, Atlas, represents an unusual giant or a typical example of a previously undetected population. David Jewett compared tracking 3I, Atlas, to glimpsing a rifle bullet for 1,000th of a second, but the analogy breaks down when considering scale. This isn't a bullet-sized projectile, but rather a mountain-sized object that somehow achieved interstellar velocities. The mechanisms capable of accelerating such massive objects to tremendous speeds challenge current understanding of stellar system dynamics and object ejection processes. The enormous size makes any potential human intercept mission even more challenging than initially calculated. Spacecraft designed for typical asteroid or comet encounters would be completely inadequate for investigating an object of this scale. Future interstellar missions might need to be redesigned to accommodate the possibility of encountering massive objects rather than small debris. The 20-kilometer scale forces humanity to reconsider both our detection capabilities and our assumptions about what travels between the stars. 3I, Atlas originates from the Milky Way's thick disk, a vertically extended region populated by the galaxy's oldest stellar populations. The object's high vertical velocity component of positive 18.5 kilometers per second relative to the Sun indicates it belongs to this ancient galactic neighborhood. Matthew Hopkins and his Oxford colleagues determined with 68% confidence that objects from the thick disk are typically between 7.6 and 14 billion years old. This connection places 3I, Atlas, among the most ancient matter ever directly observed. The thick disk association derives from detailed analysis of 3I, Atlas's galactic trajectory and velocity components. When the object arrived at our solar system, it was moving away from the galactic center with a radial velocity of -51 kilometers per second relative to the Sun. Simultaneously, its transverse velocity and vertical motion through the galactic plane created a characteristic signature matching thick disk stellar populations. This velocity profile differs significantly from thin disk objects like our Sun and most nearby stars. Thick disk stars typically contain lower concentrations of heavy elements compared to younger stellar populations, reflecting formation during earlier epochs when fewer processed materials existed in the galaxy. If 3I Atlas formed in this environment, its composition might reveal chemical signatures from the universe's early stages of stellar nucleosynthesis. Planned spectroscopic analysis will determine whether the object contains the reduced heavy element abundances expected from thick disk formation. The thick disk origin implies that 3I Atlas has been wandering through interstellar space for an extraordinarily long time. During this cosmic journey, spanning potentially billions of years, the object experienced countless gravitational encounters with stars, planetary systems, and stellar nurseries. Each encounter modified its trajectory and increased its velocity through gravitational slingshot effects, gradually building the tremendous speed we observe today. The accumulated momentum serves as a cosmic odometer recording eons of galactic wandering. Chris Lintott from Oxford University participated in computer modeling that traced 3I Atlas backward through its galactic journey. These simulations attempt to identify potential origin points within the thick disk region, though the vast timescales involved make precise source determination nearly impossible. As David Jewett noted, projecting backward from such a brief observation window to determine ultimate origins faces enormous computational challenges. The thick disk connection adds profound implications to any artificial origin hypothesis. If 3I Atlas represents technology, it would indicate that intelligent civilizations existed in the thick disk region billions of years ago. Such ancient technological civilizations would predate the formation of most planetary systems in our current galactic neighborhood. The implications stretch our understanding of when and where intelligent life might have emerged in cosmic history. The thick disk represents approximately 2/3 of the Milky Way's stellar population, making it a vast reservoir of potential source systems. However, the advanced age of thick disk stars means that many original planetary systems have likely been disrupted by stellar evolution. The parent star of 3I, ATLAS, could have evolved through its complete life cycle, possibly ending as a white dwarf, neutron star, or black hole. Any original planetary system might have been destroyed during the parent star's evolution. The thick disk trajectory also explains why 3I Atlas was difficult to detect despite its size. The object's approach direction toward the galactic center placed it against the densest star fields in our sky, where crowded background stars made detection extremely challenging. This natural camouflage allowed the object to approach relatively close before discovery, limiting our observation window for its inbound journey. The thick disk origins force us to confront deep time on a galactic scale, an object potentially older than complex life on Earth, carrying secrets from the galaxy's ancient past. Within just 1 week of beginning observations, the Allen Telescope Array amassed over 21 terabytes of data from 3I Atlas, equivalent to thousands of hours of high-resolution video. This massive dataset remains under active analysis, with SETI researchers systematically searching for both natural radio signatures and hypothetical technosignatures that might indicate artificial origin. The scope and intensity of data collection represents one of the most comprehensive attempts ever made to detect artificial signals from a specific astronomical object. Dr. Wael Farah leads the Allen Telescope Array monitoring efforts, targeting both narrowband emissions that could indicate technological signals and natural emissions from dust particles and molecular compounds. The dual approach recognizes that 3I Atlas might reveal its nature through either artificial transmissions or unusual natural radio characteristics. Natural emissions could include continuum radiation from dust and specific spectral lines from hydroxyl molecules, and other compounds typical of cometary outgassing. The search protocols specifically monitor for several types of artificial signals that would definitively indicate technological origin. Primary targets include radio communications, electrostatic discharges caused by sunlight interacting with artificial surfaces, and any evidence of maneuvering or course corrections. Active probes might attempt to maintain communication with their origin points or broadcast signals to announce their presence to potential receiving civilizations. The monitoring effort builds upon decades of SETI experience using radio telescopes for extraterrestrial intelligence searches. Projects like Serendip have analyzed deep space radio telescope data for years, developing sophisticated techniques for identifying artificial signals against cosmic background noise. The Breakthrough Listen initiative provides substantial funding and resources for comprehensive searches, making the 3I Atlas monitoring possible on an unprecedented scale. Earth's own radio emissions demonstrate how technological civilizations might be detected through their electromagnetic signatures. Over 100 years of television and radio broadcasts have created a growing sphere of artificial signals extending 200 light-years from Earth. These signals would be easily recognizable as artificial due to their repetitive nature and narrow bandwidths, providing a template for identifying similar emissions from other technological sources. Radio communication across interstellar distances requires sophisticated antenna systems and signal processing techniques. Even powerful transmitters face tremendous signal degradation over cosmic distances, making reception challenging without large, sensitive antenna arrays. The Allen Telescope Array's 34-meter dishes provide the sensitivity needed to detect weak signals from objects at 3I Atlas's distance. Initial analysis of the 21-terabyte dataset has not revealed obvious artificial signals, but data processing continues. The massive volume of information requires careful analysis using sophisticated algorithms designed to identify subtle patterns that might indicate technological origin. Modern SETI techniques employ artificial intelligence systems to process large datasets and identify candidate signals for human verification. The monitoring campaign will continue throughout 3I Atlas's approach to perihelion and beyond. If the object represents artificial technology, signal characteristics might change as it approaches the Sun and potentially activates dormant systems. Loeb's team will intensify monitoring after the October 29th perihelion passage, searching for signals that might indicate probe deployment or course corrections. The radio silence thus far doesn't eliminate the possibility of artificial origin. The dark forest hypothesis suggests that advanced civilizations might deliberately maintain radio silence to avoid detection by potentially hostile neighbors. If 3I Atlas represents technology from such a civilization, it might remain deliberately quiet until completing its reconnaissance mission. 21 terabytes of cosmic data hold secrets that might reshape humanity's understanding of our place in the universe. 3. Atlas follows a trajectory, coincidentally, aligned with the orbital planes of our solar system's planets, creating what astronomers call ecliptic alignment. Specifically, the object's path tilts 175 degrees with respect to the ecliptic, retrograde motion, inclined only 5 degrees from the planetary orbital plane. This close alignment represents a rare 0.2% probability occurrence for randomly arriving interstellar objects. The mathematical odds against such precise alignment occurring by chance force uncomfortable questions about intentional targeting. The retrograde nature of 3I Atlas's approach means it travels opposite to the direction of planetary motion around the Sun. At perihelion, the object will achieve a speed of 68 kilometers per second relative to the Sun, while Earth orbits at 30 kilometers per second in the opposite direction. This creates a relative velocity difference of 98 kilometers per second between Earth and 3I Atlas, speeds that make any human intercept mission completely impractical using current rocket technology. The ecliptic alignment allows 3I Atlas to encounter multiple planets during a single solar system passage. The precisely calculated trajectory brings the object within 0.65 astronomical units of Venus, 0.19 astronomical units of Mars, and 0.36 astronomical units of Jupiter. The cumulative probability of such close encounters with multiple planets, given random arrival timing, calculates to only 0.5%. Natural interstellar objects lack the ability to plan and execute such mathematically precise multiplanetary approaches. The alignment enables comprehensive reconnaissance of the solar system's major worlds during a single flyby mission. Any artificial intelligence controlling 3I Atlas could gather detailed information about planetary characteristics, atmospheric compositions, and potential habitability during these close approaches. The trajectory also creates opportunities for deploying smaller probes toward individual planets during each encounter. The orbital alignment provides strategic advantages for spacecraft observations from multiple vantage points. Mars-based instruments will have clear views during 3I Atlas's approach when Earth-based telescopes cannot observe due to solar glare. The Jupiter encounter allows the Jupiter Icy Moons Explorer and other outer system missions to track the object from completely different perspectives. This multi-platform observation capability could reveal details invisible from any single location. The precise ecliptic alignment also explains why 3I Atlas remained undetected until July, despite its enormous size. The object's approach direction toward the galactic center placed it against dense star fields where detection becomes extremely difficult. This natural camouflage effect allowed the object to approach relatively close before discovery, limiting observation time for analyzing its inbound trajectory. The alignment timing creates perfect conditions for potential course corrections during the hidden perihelion passage. The solar eclipse period provides 3 months when any maneuvering would be invisible from Earth. A reverse Oberth maneuver during this period could slow the object enough to achieve gravitational capture within our solar system. Such timing suggests planning rather than coincidence. Future interstellar missions might benefit from studying 3I Atlas's trajectory optimization. The European Space Agency's planned Comet Interceptor mission could potentially learn from the efficient multi-planetary approach demonstrated by this visitor. Whether natural or artificial, 3I Atlas provides a masterclass in solar system navigation. The perfect orbital alignment forces a choice between accepting astronomical improbability or acknowledging the possibility of deliberate trajectory planning by an intelligence capable of comprehensive solar system analysis. On November 16, 1974, the Arecibo radio telescope broadcasted humanity's first deliberate interstellar message toward the globular cluster Messier 13, located 200 light-years away. Created by renowned SETI researcher Frank Drake and scientific communicator Carl Sagan, this graphic message showcased humanity's technical advancement and announced our presence to potential cosmic neighbors. The Arecibo message has remained the most widely publicized effort to contact extraterrestrial intelligence in the 48 years since its transmission. What if something was listening from much closer than we imagined? The broadcast utilized Arecibo's megawatt transmitter, coupled with its massive 305-meter antenna, creating a tremendously powerful signal capable of reaching across thousands of light-years. The transmission targeted about 300 stars within the M13 cluster, positioned toward the outskirts of our Milky Way galaxy. However, the 25-year travel time to reach the target and another 25 years for any response means humanity would wait 50 years for a reply from M13. But what about objects already traveling through our cosmic neighborhood? Earth's inadvertent radio transmissions began much earlier than the deliberate Arecibo broadcast. The first public radio broadcast occurred on December 24, 1906, and these signals have been traveling outward into space for over 100 years. Currently, these television and radio broadcast signals extend approximately 200 light-years from Earth in a growing sphere of artificial electromagnetic radiation. Any intelligence within this sphere could have detected our presence decades ago. These signals would be easily recognizable as artificial due to their repetitive nature and narrow bandwidths. Earth's radio emissions provide a clear template for how technological civilizations announce themselves through electromagnetic radiation. The signals have already reached over 10 nearby stars, including notable targets like Vega, Aldebaran, Barnard's star, Sirius, and Proxima Centauri. If intelligent life exists around any of these stars, they could have been listening to human broadcasts for decades. The timing becomes unsettling when considered alongside 3I, Atlas's ancient journey. If the object has been wandering the galaxy for billions of years, it could have been positioned to detect Earth's early radio signals. The tremendous speeds achieved during its cosmic journey suggest gravitational encounters with numerous stellar systems, encounters that could have altered its trajectory towards signal sources. Our century of broadcasts might have served as an inadvertent beacon, attracting interstellar attention. Beyond the Arecibo message, humanity has transmitted numerous other deliberate interstellar communications. Soviet attempts included transmissions to Venus, encoded with Mir, Lenin, and USSR in Morse code. More recent efforts between 1999 and 2016 sent signals to stars 17 to 69 light-years away. Researchers worldwide are now developing the Beacon in the Galaxy message, combining elements from all previous METI attempts. The dark forest hypothesis adds chilling implications to our broadcast history. If the galaxy contains hostile civilizations that eliminate potential threats, our radio signals might have inadvertently painted a target on Earth. The hypothesis suggests that civilizations remain silent to avoid detection by predators, but humanity has been broadcasting its location for over a century. 3I, Atlas, might represent either a response to our signals or reconnaissance preceding more direct contact. Loeb suggests that if 3I, Atlas, proves artificial, humanity should consider attempting radio communication during its approach. However, he warns that such communication carries significant risks. An alien intelligence might perceive our signals as threats and respond defensively. Unlike distant radio communications that take thousands of years to travel, 3I, Atlas, could respond within months or reach Earth by Christmas 2025. The Arecibo echo might not be the distant reply we expected, but rather the approaching shadow of something that has been listening all along. Both Voyager 1 and Voyager 2, launched in 1977, carrying golden records, phonograph discs, intended to communicate humanity's story to any extraterrestrial intelligence that might encounter the spacecraft. Like their predecessors, Pioneer 10 and 11, with their simple plaques, the Voyager missions carry messages from Earth as they journey into interstellar space. Created under Carl Sagan's leadership, these records contain 116 images, natural sounds, spoken greetings in 55 languages, and musical selections representing human culture. The golden records serve as time capsules carrying humanity's message to the cosmos. Voyager 1 has achieved the remarkable distinction of becoming the first human-made object to enter interstellar space, crossing the heliopause on August 25, 2012. Both Voyager spacecraft have now reached the region between stars, where galactic plasma is present, carrying their golden messages into the same interstellar medium that 3I, Atlas, has been traversing for potentially billions of years. The probe continues to transmit scientific data, though signals now take over 22 hours to reach Earth due to its tremendous distance. The golden record contents were carefully selected to represent Earth's diversity and human achievement. Instructions for playing the record are encoded on the cover, along with a pulsar map and hydrogen molecule diagram to help recipients locate Earth. The 116 images include mathematical concepts, human anatomy, technological achievements, and natural phenomena, while the audio portion contains greetings, music, and sounds of Earth. A spoken greeting in English by United Nations representatives announces humanity to the cosmos. Recently, Voyager 1 has experienced concerning communication problems that eerily parallel the mysterious nature of 3I, Atlas. Since November 2023, the spacecraft has been transmitting unreadable data streams, though engineers successfully decoded meaningful signals in March 2024. The decoded message contained a complete readout of the flight data subsystem memory, allowing NASA to diagnose the communication problems. The probe's signals take 22.5 hours each way to reach Earth, making real-time troubleshooting impossible. Voyager's communication system demonstrates the technological requirements for interstellar messaging. The spacecraft uses 23-watt radios, transmitting through 3.7-meter antennas to 34-meter dishes on Earth. Despite the low transmission power, careful antenna design and signal processing allow communication across billions of miles. The system operates in S-band and X-band frequencies, providing data rates that decreased as distance increased but still maintain contact. The Pioneer and Voyager missions established important precedents for interstellar communication. The Pioneer plaques featured mathematical concepts, human figures, and pulsar maps designed to be understandable to any technological civilization. The visual representation of humans from the Pioneer plaques has been reused in subsequent messages, including the cosmic call radio transmission. These consistent design elements create a recognizable signature for human communication attempts. Both spacecraft will continue their interstellar journeys for potentially millions of years, carrying humanity's messages into regions where other interstellar travelers like 3I, Atlas, have wandered. Over the next 1,000, million, and billion years, these probes will explore our universe along with our human legacy. Whether humans still exist when the probes encounter other intelligence remains unknown, but the messages will continue traveling regardless. Carl Sagan wrote that the golden record represents a present from a small, distant world, a token of our sounds, our science, our images, our music, our thoughts, and our feelings. The record concludes with the message: "We are attempting to survive our time, so we may live into yours." Now, as 3I, Atlas approaches from the same interstellar void that Voyager has entered, we must consider whether our messages have already found their intended audience. The golden records travel outward, while 3I, Atlas, approaches inward, two ships passing in the cosmic night, carrying messages across the dark. Pioneer 10 launched in 1972 as NASA's first mission to the outer planets, followed by Pioneer 11 1 year later. After successful exploration of Jupiter and Saturn, both spacecraft continued their journeys into deep space, carrying humanity's first deliberate messages to potential extraterrestrial intelligence. The Pioneer plaques, designed by Carl Sagan and mounted on the spacecraft exteriors, serve as cosmic postcards announcing our species to anyone who might encounter these wandering ambassadors. Until recently, Pioneer 10 held the distinction of being the most distant human-made object from Earth. The plaques feature carefully designed symbols intended to be universally understandable to any technological civilization. Key elements include a pulsar map showing Earth's location relative to 14 pulsars, a hydrogen molecule diagram establishing universal measurements, and line drawings of naked human figures. The significance of the human couple illustration is demonstrated by its reuse in later messages, including the cosmic call radio transmission. These consistent design elements establish recognizable signatures for human communication attempts. The visual and mathematical approach reflects the assumption that physics and mathematics provide universal languages for interstellar communication. Researchers believe that any technological civilization would understand concepts like hydrogen transitions, pulsar periods, and basic geometric relationships. The Pioneer design principles influenced all subsequent human messages to space, establishing templates for how to communicate across species and stellar distances. Pioneer 10 maintained its distance record until February 17, 1998, when Voyager 1 overtook it at 69 astronomical units from the Sun. Currently traveling at approximately 17 kilometers per second, Voyager 1 has the fastest heliocentric recession speed of any spacecraft. However, All four pioneering spacecraft, Pioneers 10 and 11, plus Voyagers 1 and 2, now carry human messages into the same interstellar medium that 3I, Atlas, has been traversing. The progression from Pioneer plaques to Voyager golden records demonstrates humanity's evolving approach to interstellar communication. While Pioneer offered basic information about human appearance and Earth's location, Voyager provided comprehensive cultural content, including music, languages, and detailed imagery. Current efforts, like the Beacon in the Galaxy message, combine elements from all previous attempts, suggesting refinement of our communication strategies. The irony becomes apparent when considering that human probes traveling at 10 meters per second would be virtually impossible to detect if they represented alien technology visiting our solar system. Current detection capabilities can track objects down to 10 or 20 meters in size, only out to Jupiter's distance. If an alien probe similar to our Voyager spacecraft approached from interstellar space, we probably wouldn't spot it until it reached the asteroid belt. This limitation suggests that numerous small interstellar visitors might pass undetected. The Pioneer and Voyager missions will continue their cosmic journeys for potentially billions of years, carrying humanity's earliest attempts at interstellar diplomacy. These spacecraft represent our species' first steps into the galactic community, announcing our technological capabilities and peaceful intentions. The messages they carry establish precedents for how emerging civilizations might introduce themselves to the cosmic neighborhood. Now, as 3I, Atlas approaches with characteristics that challenge natural explanations, we must consider whether our pioneering postcards have already been received and analyzed. If the interstellar visitor has been wandering the galaxy for billions of years, it could have encountered evidence of numerous technological civilizations, including potentially humanity's expanding sphere of radio emissions. The synchronized timing of 3I, Atlas's arrival, with our era of space exploration and interstellar messaging, might not be coincidental. The Pioneer postcards sail outward through the dark, while something ancient and mysterious approaches from the same cosmic void, a meeting arranged across the vastness of space and time. Earth has been broadcasting artificial radio signals into space for over 100 years since the first public radio transmission on December 24, 1906. These television and radio broadcasts now form an expanding sphere of electromagnetic radiation, extending approximately 200 light-years from our planet. The signals have reached over 10 nearby stars, including prominent targets like Vega, Aldebaran, Barnard's Star, Sirius, and Proxima Centauri. Any intelligence within this growing sphere could have detected clear evidence of technological civilization on Earth decades ago. These inadvertent broadcasts would be easily recognizable as artificial due to their repetitive nature and narrow bandwidths. Human television and radio emissions create distinctive patterns that differ dramatically from natural cosmic radio sources. The signals provide a clear template for how technological civilizations announce themselves through electromagnetic radiation, whether intentionally or accidentally. Our planet has been essentially shouting its presence to the cosmos for an entire century. The detectability of Earth's signals demonstrates how vulnerable technological civilizations become to observation by advanced neighbors. If intelligent alien life exists on planets orbiting nearby stars, these signals could be heard and deciphered despite some garbling by Earth's ionosphere. The unintentional nature of most transmissions means that civilizations reveal themselves long before they consciously attempt interstellar communication. We became visible to cosmic neighbors before we realized we were broadcasting. The timing correlation with 3I, Atlas's approach, creates unsettling implications. If the object has been wandering through interstellar space for billions of years, its trajectory could have been modified by gravitational encounters to investigate signal sources. Each stellar encounter during its cosmic journey added momentum while potentially altering its direction toward electromagnetic anomalies, like Earth's radio emissions. Our century of broadcasts might have served as an inadvertent homing beacon. The progression of human signal technology reveals our advancing capabilities to any listening intelligence. Early radio broadcasts gave way to television transmissions, then satellite communications, radar systems, and deliberate interstellar messages like the Arecibo broadcast. This technological evolution creates a timeline readable by external observers, revealing how quickly human civilization has developed space-age capabilities. The signal progression maps our species' rapid advancement from primitive radio to space exploration. Current deep space network capabilities demonstrate the sophistication required for interstellar monitoring. The network employs large antenna arrays and sensitive receivers capable of detecting extremely weak signals across vast distances. These same technologies that allow us to communicate with distant spacecraft could be used by advanced civilizations to monitor our planet's electromagnetic emissions. The tools we use to explore space also make us detectable to cosmic observers. The dark forest hypothesis adds terrifying context to our broadcast history. If the galaxy contains predatory civilizations that eliminate potential threats, our radio signals might have inadvertently marked Earth as a target. The hypothesis suggests that wise civilizations remain silent to avoid detection, but humanity has been announcing its presence for over a century. 3I. Atlas might represent reconnaissance, preceding more direct contact, or worse, threat assessment before elimination. Loeb warns that attempting radio communication with 3I, Atlas carries significant risks compared to distant SETI targets. Unlike signals to star clusters thousands of light years away, communication with this nearby visitor could prompt immediate responses. Any intelligence controlling 3I ATLAS could reach Earth within months rather than millennia, making first contact scenarios potentially imminent rather than theoretical. Future interstellar messaging efforts, like the Beacon in the Galaxy, continue humanity's tradition of cosmic communication. These deliberate transmissions join our century of inadvertent broadcasts in creating an ever-expanding announcement of human presence. Whether our messages attract friendly neighbors or dangerous predators remains the ultimate gamble of interstellar communication. 2 centuries of human signals have painted a target on Earth that cannot be erased, and something ancient and mysterious is approaching to investigate. Voyager 1 now transmits from interstellar space, having crossed the heliopause boundary on August 25, 2012. Making it the first human-made object to enter the region between stars. The spacecraft continues operating after almost 50 years, though signals require over 22 hours to reach Earth due to its tremendous distance of more than 24 billion kilometers. It travels at approximately 197 kilometers per hour, covering about 523 million kilometers per year, roughly 1 light-year every 18 years. Voyager has entered the same cosmic realm that 3I, Atlas has been traversing for potentially billions of years. Recent communication anomalies with Voyager 1 have created unsettling parallels to the mysterious nature of 3I, Atlas. Since November 2023, the spacecraft transmitted unreadable data streams, binary patterns of alternating ones and zeros, replacing normal telemetry. NASA engineers described the situation as maintaining a connected call, while Voyager's voice was replaced with a monotonous dial tone. In March 2024, engineers successfully decoded meaningful signals containing complete memory readouts from the flight data subsystem. Voyager's radio communication system was designed for use beyond the solar system's limits, employing a 3.7-meter high-gain antenna to communicate with Earth's deep space network. The spacecraft normally transmits on channel 18 using frequencies of either 2.3 or 8.4 GHz, while receiving commands at 2.1 GHz. When unable to communicate directly, the digital tape recorder can store approximately 67 kilobytes of data for later transmission. The communication delays of 22.5 hours each way make real-time problem-solving impossible. Voyager carries the golden record, containing humanity's message to any cosmic intelligence that might encounter the spacecraft during its eternal journey. The record includes 116 images, natural sounds, spoken greetings in 55 languages, and musical selections representing Earth's cultural diversity. Carl Sagan wrote that the record represents a present from a small, distant world, with the message, "We are attempting to survive our time, so we may live into yours." The golden record serves as humanity's ambassador to the interstellar medium. The spacecraft's radioisotope thermoelectric generators originally produced 470 watts of electric power at launch, though output gradually decreases as the plutonium fuel decays. Current projections suggest the mission can continue returning scientific data until at least 2025, with possible engineering data transmission until 2030. The probe's remarkable longevity demonstrates the engineering excellence required for interstellar missions. Thinking, what makes interstellar objects like 3I, Atlas, so fascinating to study from a scientific perspective and potentially concerning from a security perspective? Voyager 1's recent communication problems add an eerie synchronicity to the arrival of 3I, Atlas. Since November 2023, the spacecraft has been transmitting garbled data streams, repeating patterns of alternating ones and zeros instead of meaningful telemetry. NASA engineers described the situation as maintaining a connected phone call, while the spacecraft's voice was replaced with a monotonous dial tone. The timing coincides unsettlingly with increasing awareness of 3I, Atlas, approaching our solar system. In March 2024, engineers achieved a breakthrough by decoding meaningful signals from the corrupted data stream. The decoded message contained a complete readout of the flight data subsystem memory, including operational codes and spacecraft status information. However, the communication challenges continue due to the enormous distances involved. 2AN signals require 22.5 hours each way between Earth and the spacecraft. Every troubleshooting command sent to Voyager requires nearly 2 full days for confirmation of results. The communication anomaly apparently originated from a failed chip in the flight data subsystem, possibly damaged by space radiation or simply worn out after 48 years of operation. Engineers believe the damage prevents normal data packaging before transmission to mission control. While the technical explanation seems plausible, the timing of these problems coinciding with 3I, Atlas's discovery, creates uncomfortable questions about potential interference. Thinking, let me correct that and continue with the script properly. Voyager 1's recent communication problems add an eerie synchronicity to the arrival of 3I, Atlas. Since November 2023, the spacecraft has been transmitting garbled data streams, repeating patterns of alternating ones and zeros instead of meaningful telemetry. NASA engineers described the situation as maintaining a connected phone call, while the spacecraft's voice was replaced with a monotonous dial tone. The timing coincides unsettlingly with increasing awareness of 3I, Atlas, approaching our solar system. In March 2024, engineers achieved a breakthrough by decoding meaningful signals from the corrupted data stream. The decoded message contained a complete readout of the flight data subsystem memory, including operational codes and spacecraft status information. However, the communication challenges continue due to the enormous distances involved. Signals require 22.5 hours each way between Earth and the spacecraft. Every troubleshooting command sent to Voyager requires nearly 2 full days for confirmation of results. The communication anomaly apparently originated from a failed chip in the flight data subsystem, possibly damaged by space radiation or simply worn out after 48 years of operation. Engineers believe the damage prevents normal data packaging before transmission to mission control. While the technical explanation seems plausible, the timing of these problems coinciding with 3I, Atlas's discovery, creates uncomfortable questions about potential interference. Could an approaching interstellar visitor be affecting our most distant spacecraft? Voyager 1 operates in the same interstellar medium that 3I, Atlas, has been traversing for potentially billions of years. Both objects now exist in the region between stars, where galactic plasma and cosmic radiation create challenging electromagnetic environments. The spacecraft's instruments continue studying solar system boundaries and interstellar conditions that 3 Atlas would have experienced throughout its cosmic journey. These shared environmental conditions create possibilities for indirect interaction or interference. Amateur radio operators have successfully tracked Voyager 1's signals using ground-based equipment, demonstrating that the spacecraft's transmissions can be detected by relatively simple technology. In March 2006, German AMSAT operators used a 20-meter dish at Bochum to receive and verify Voyager data against official Deep Space Network stations. This accessibility suggests that any advanced intelligence could easily monitor our most distant spacecraft's communications. Voyager's communication system relies on precise antenna pointing and signal processing to maintain contact across interstellar distances. The spacecraft uses a 23-watt radio transmitter, higher than typical cell phone power, but still requiring enormous ground-based antennas to receive signals. Earth stations employ 34-meter dishes and extremely sensitive amplifiers to decode the faint signals from billions of miles away. Any disruption to this delicate communication link could originate from numerous sources. The recent communication restoration provides hope that Voyager can continue its mission despite the hardware failures. Engineers plan to reposition and synchronize remaining code sections to restore normal data transmission capabilities. However, the aging spacecraft operates far beyond its original design life, making future failures increasingly likely. Each repair attempt requires extreme patience due to the 45-hour round-trip communication delay. The parallel timing of Voyager's communication problems and 3I, Atlas's approach, might represent more than coincidence. If 3I, Atlas, contains advanced technology, it might be scanning our solar system's electromagnetic environment, potentially interfering with existing communication systems. Such reconnaissance activity could affect sensitive equipment like Voyager's aging electronics. The possibility remains speculative but troubling. Voyager carries humanity's golden record message into the same interstellar realm where 3I, Atlas, has wandered. The spacecraft represents our species' first ambassador to the cosmic community, broadcasting our peaceful intentions through both its scientific mission and cultural cargo. If 3I, Atlas, represents a response to human signals, Voyager's status as our interstellar emissary makes it a natural target for investigation or communication attempts. The whispers from Voyager grow stranger as something ancient approaches from the dark, two messengers from different worlds passing in the interstellar.